Okay, let's discuss assignment 2 of semester 2. There are 4 questions in this assignment. Question 1, you are given hydrocarbons A and B and also their molecular formula. So A C4H10, B C4H8. By looking at the formula, okay, we can tell that A is a saturated hydrocarbon. Okay, B is an unsaturated hydrocarbon. So that means A is alkane and B is alkene, right? Because the general formula for alkane will be CnH2n plus 2 and alkene will be CnH2n. Right, both of them are unbranched. Okay, very important, this point. A does not decolorize bromine, so this statement confirms that A is actually an alkane. B decolorizes bromine and shows geometrical isomerism. So B has a double bond and it decolorizes bromine, again confirms that B is an alkene. Now part A of this question tells us to draw the skeletal formula of A. Okay, so since A is actually an alkane without a branch, so let's draw a 4-carbon alkane. There's no branch. I will draw the display formula first. Okay, then later we can turn it into the skeletal formula. So 4 carbon, all hydrogen atoms bonded to carbon atoms. Okay, no other element. So I'll put 4 dots, every 1 dot representing a carbon atom. Then I just join all of them together. So this will be the structure of A. Okay, correct. So this is the answer. Now, part B of this question tells us that the hydrocarbon A, okay, which is unbranched, has another isomer that is branched. So, isomer means same molecular formula, but different structure, right? So, this time I'm going to draw another isomer of A, also 4 carbon, but with a branch. Okay, so I'm going to just put this branch at carbon number 2 because the branch should only be bonded to carbon number 2. There's only 4 carbon, okay? So 3 carbon in the straight chain, in the skeleton. So another one will be a branch CH3 bonded to carbon number 2. So this is a branch isomer of A. So it looks like this. This is the isomer. So A is okay, A is more linear compared to this branch isomer. Imagine I have a lot of molecules A, okay, and they're all stacked together, very close to each other. So there are so many points that they are in contact along this whole chain. While the isomer of A looks more spherical because of the branch. So between the molecules, you have less contact points. So more contact points will have stronger molecular force, intermolecular forces between the molecules. Okay, the one that is more spherical, less contact points, so weaker interaction between the molecules, weaker intermolecular forces. Right. So that is the reason why unbranched A has higher boiling point compared to its branch isomer. So how do we answer this? Okay, first you compare, right? A and the isomer. A has higher boiling point. So why? Okay, because A molecule between molecules of A, okay, they are stronger stronger ID forces. And the reason is because it has more points of contact, okay, between the molecules in hydrocarbon A. Okay? Or you can use reverse argument here. ORA means or reverse argument. You can say that B has weaker ID forces because B has less points of contact, okay, between the molecules. Okay, now let's look at part C and D of question 1. This time we are talking about molecule B, hydrocarbon B. So part A and B was about hydrocarbon A. Now, part C, we are supposed to give the structural formula of B. Again, B, alkene, 4 carbon alkenes, okay, unbranched. So let's draw the structure of an unbranched, okay, alkene with 4 carbon. So I can have the double bond between carbon number 1 and number 2. Display formula first, yeah, before we turn it into a structural formula. So the double bond can be between carbon 1 and 2 or between carbon 2 and 3. Okay, later we will check the other part of the information to find out which one should be the formula of B. Now, B decolorizes bromine and shows geometrical isomerism. So any of these can be B, but the one that shows geometrical isomerism will be, okay, the correct structure of B. Now let's check the first structure. I look at the 2 carbons sharing the double bond. To show geometrical isomerism, an alkene must have the 2 carbon sharing a double bond, each of them bonded to 2 different groups of atoms. So let's look at this carbon number 1. Okay, it is bonded to 2 hydrogen, not different groups of atoms, right? Then okay, immediately we know that this is not B. Let's check the structure number, this second structure. So again, carbon number 1, carbon number 2. Now, carbon number 1 bonded to hydrogen, bonded to a CH3. 2 different groups of atoms. Now, let's check the second carbon, carbon number 2, bonded to hydrogen and CH3. Again, 2 different groups of atoms. So, this molecule will show cis-trans isomerism. This is the structure of B. Now, let's write structural formula from this display formula. I'll start from the left, CH3, CH, double bond, CH, and then CH3. Okay, so this is the structural formula of B. Now they ask us to explain why B shows geometrical isomerism. Okay, alkenes with the 2 carbon bonded to different groups of atoms can show geometrical isomerism is because there is no free rotation about the C double bond. Okay, so now let me show you the answer scheme. Structural formula of B, which is what we have written just now. Now explain why B shows geometrical isomerism. No rotation, okay, no rotation of C double bond, or restricted rotation, limited rotation of the C double bond. Okay, or they accept that, okay, each carbon in the C double bond, they are bonded to 2 different groups of atoms. One of them is methyl group, the other one is hydrogen atoms. Okay, now part E, we are supposed to draw the mechanism of the reaction of B with bromine. Now alkenes will react with bromine. Okay, so I'll use a general alkene structure. So it will react with bromine and we will get, okay, a dibromoalkene like this. Okay. Now we are supposed to draw the mechanism. The name of this mechanism is electrophilic addition. Okay. So start with the structure of B, right? If you cannot remember the structure of B, you can always go back to the previous answer to look at the structure of B. Now, alkene, then we have the Br2. Okay. Now, this Br2 is a non-polar molecule. But, okay, when it comes near the double bond of this alkene, this double bond has 4 electrons, a lot of electrons. So when this Br2 approaches this double bond, the electrons from this double bond and the electrons in Br2 molecule will repel one another. So the electrons on this side, they feel the repulsive forces from the double bond, okay, and will go to the other side of the molecule. So this double bond induce a dipole in the bromine molecule. And now this bromine molecule, okay, will have partial charges. Before that, let me erase this drawing so that I can show you the mechanism correctly. Okay, right, let's go back to the drawing. So induce, okay, dipole in this bromine molecule. Now bromine molecules has partial charges. So the one that is nearer to the double bond, right, is more partial positive. The one that is further away from the double bond is partial negative. Now, after that, we can draw, okay, the mechanism just like how we draw the mechanism of electrophilic addition for other electrophile. So this double bond, okay, arrow from the double bond to the partial positive Br, okay, this will be broken. Both the electrons will be taken by the partial negative Br. Then an intermediate will form. Okay. A new bond is formed between the C and the Br. Okay. The carbon on the right hand side, okay, still have the H and CH3, and then a positive charge on this carbon. So a carbocation ion is formed. Now remember this Br took both the electrons, right? Now it has, okay, lone pair with a negative charge. So a bromide ion is actually formed from the breaking of this bond. Now this lone pair will be accepted by the positive carbon. So at the end, okay, both the carbon initially sharing double bond one, now no more double bond, and both of them are bonded to a Br, bromine. Right? So this is how you should draw, okay, the mechanism for electrophilic addition. Okay. Now you see part F, you are asked to explain the origin of the dipole in Br2 in this mechanism. Because Br2 should be a non-polar molecule, okay, its dipole was induced by the pi electrons in this alkene molecule. Now let's go and look at the answer scheme. So for drawing of the mechanism, there are 4 marks. First mark goes to arrow from the C double bond to the partial positive bromine, this arrow. Okay. Second mark goes to the dipole on the bromine. Incorrect orientation means the partial positive bromine should be closer to the double bond. Because electrons are negatively charged, and this bromine is partial positive, negative charge and positive charge, they attract each other. So the partial positive bromine should be nearer to the double bond. Now, and also arrow from the Br bond to the partial negative Br, this arrow. So second mark is for, okay, correct orientation, dipole in Br, correct orientation, and then arrow from the bond to the partial negative Br. Now, third mark will be correct carbocation ion. The intermediate must be correct. One of the carbon is positive. And also, you have the ion, bromine ion from the structure with the CC drawn. Okay, you have this. Last one, you have bromide ion with lone pair. Must show at least one lone pair because this partial negative bromine took both the electrons from the bond. Okay, so this lone pair will later be accepted by the positive carbon, negative charge on the bromide ion, and also the arrow from the lone pair to the carbon atom, the positive carbon atom of the intermediate. 4 marks for the mechanism. Now, in every exam paper, there will be a question asked, okay, on drawing the mechanism. There are 5 types of mechanism in your AS syllabus. Number 1, free radical substitution of alkane. Number 2 is this electrophilic addition of alkene. Okay. Number 3 and number 4 will be nucleophilic substitution of halogenyl alkane, SN1, SN2. And the last one will be nucleophilic addition of carbonyl compound. Okay, in every paper, test paper, exam paper, your actual paper too, one of these will come out in the question. So make sure that you know all these mechanisms before you enter the exam hall for any assessment. Right, now let's look at part F. Explain the origin of dipole on Br2 in this mechanism. Okay, electrons in the pi bond induce the dipole. Okay, that was what I was explaining to you. Okay, there are more explanations here. You can read them. Okay, you can write high electron density in pi bond. Okay, so repels the electrons away from the nearest Br. Okay, that's why induce a dipole. Okay, or you can talk about the polarization of this bromine molecule by the high electron density in pi bond. So any of this answer, okay, the one that I explained to you was the first one because I think that is the simplest explanation. Alright, that will be the end of question 1. Now let's look at question 2. Question 2 is about alcohol C and D. Okay, molecular formula again given. Both isomers are branched. So this one they tell you very clearly, okay, both of them are branched. And branched alcohols with this formula can be 2-methylpropan 1-ol or 2-methylpropan 2-ol. Right, this is 2-methylpropan 2-ol. Okay, 2-methylpropan 1-ol will look like this. Okay, let me write the name maybe here. So these two are the branched alcohol with C4H10OSD molecular formula. Now let's look at more information about C and D. So when C is heated under reflux with acidified, okay, potassium dichromate 6, no color change is observed. No color change, okay, not oxidized, this is oxidizing agent. C is not oxidized by oxidizing agent. C cannot be oxidized. C is a tertiary alcohol. So between 2-methylpropan 2-ol and 2-methylpropan 1-ol, okay, this is the tertiary alcohol. Okay, 2-methylpropan 1-ol is a primary alcohol. Now, how do I know? Okay, this carbon that's bonded to the OH is bonded to 3 alkyl groups. So tertiary alcohol. Primary alcohol because the carbon that is bonded to the OH is bonded to only 1 alkyl group. So C is tertiary alcohol. C is the 2-methylpropan 2-ol. So this is the structure of C. Now, D is just another branch alcohol with the same molecular formula. So since C is 2-methylpropan 2-ol, D will be 2-methylpropan 1-ol. Sorry. Okay. H, H, O, H. Now let's look at more information about D. When D is heated under reflux with acidified potassium dichromate, the color of the mixture changes from orange to green. Yes, it is oxidized. Therefore, the oxidizing agent changed color from orange to green. Then when this oxidation occurs, E is formed. Oxidation of D forms E. Now, D is primary alcohol, so it can be oxidized to aldehyde, okay, or carboxylic acid. Let's look at the molecular formula of E. Right, C4H8O2, 2-oxygen. If it is an aldehyde, okay, its functional group is CHO. Okay, if it is carboxylic acid, the functional group is COOH. So COOH is the functional group with the 2-oxygen. So from there, I know that E is actually a carboxylic acid. If you still didn't get this clue from the molecular formula, you can read, okay, the reaction of E. Now, E reacts with aqueous sodium carbonate to form carbon dioxide gas. Okay, only acid will react with sodium carbonate to form carbon dioxide gas. So, aldehyde and carboxylic acid is the acidic compound. So, again, confirm that E is a carboxylic acid. Now, let's turn this compound D, okay, oxidize this compound D to form a carboxylic acid. So this part of the molecule will become COOH. Okay, the rest of the molecules will remain unchanged in oxidation because the other parts are hydrocarbon. Okay, they don't undergo oxidation. So this will be the structure of E, a carboxylic acid. Okay, so this is the answer scheme just to confirm that we got all the structures correct. Now if you get all 3 correct, you'll be awarded 2 marks. 2 correct, only 1 mark. Then okay, we are asked to write the equation for the reaction between E and aqueous sodium carbonate. So this is the structure of E. Okay, so let's write this equation. CH3. Now, I think that it is easier to write equation using the structural formula. So I'm going to turn this into a structural formula. E reacts with sodium carbonate. I will get a carboxylate salt, sodium carboxylate, yeah. CHCO negative and A positive with CO2. That means I will need 2 of these because I have 2 and A. So 2 to balance the equation. And we have one more byproduct, H2O. Right, so this will be the equation for the reaction between E and aqueous sodium carbonate. All right, that was the end of question 2. Now we look at question 3. Question 3, we have another 2 isomers, F and G, with the molecular formula C5H10O. Okay, both of them form orange precipitate when reacted with 2,4-DMPH. So this one tells us that both F and G, they are carbonyl compounds. So one of them could be aldehyde, okay, and then another one could be ketone. Or both of them aldehyde, both of them ketone. Okay, we do not know yet. Let's just look at their reactions. Okay, F is unbranched, okay, no branch, reacts with alkali aqueous iodine to produce a yellow precipitate. Only carbonyl compound with CH3CO structure in the molecule can react with alkali aqueous iodine to produce a yellow precipitate. So F is unbranched. Okay, F is unbranched. So that means F5 carbon, okay, must have this structure in the molecule. So just start from the left hand side, CH3CO, okay, and the rest will be LQ group. So this is the structure of F. Okay, here, right? The answer scheme, which is correct, matches the structure that we solved. Now, G does not react with alkaline aqueous iodine. So G will not have this partial structure in the molecule. Okay, the C double bond O will not be bonded to any CH3 group. Okay, so just draw the C double bond O first. Okay, left and right. Okay, left hand side cannot be CH3, right hand side cannot be CH3 also. Now, it contains a chiral center. So I need to use another 4 carbon, okay, to create a chiral center. So let's say this C is bonded to hydrogen. Okay, it's bonded to a C double bond O and R here. Okay, 2 different groups of atoms. Chiral center means must be bonded to 4 different groups of atoms. So I have 1 group, 2 groups. Okay, let's create more. Okay, 3 groups, and then the 4th one I'll put CH2CH3. So 1, 2, 3, 4. Okay, now I have 4, sorry, 5. 1, 2, 3. Right, now I have 1, 2, 3, 4, 5. 5 carbon. I used up all the 5 carbons in the molecular formula. So I still have 3 plus 3, 6, 7, 8, 9. Okay, 1 more hydrogen. So that shows us that G is actually, okay, an aldehyde, which matches this description. It produces a silver mirror when warmed with Tollens reagent. This part, okay, is the aldehyde functional group. Now let's write this in structural formula format. So CHO, CHO, okay, CH, CH here, a branch, CH3, and C2H5. So this is the structure of G. Now, the next part is you're supposed to explain the meaning of the term chiral center. Okay, very straightforward. Okay, a carbon atom that is bonded to, that's attached to 4 different groups of atoms. That will be a chiral center. All right, now let's look at the last question, question 4. Okay, again, it is about 2 isomers. Okay, this time H and I. Now, both H and I, they have molecular formula of C2H4O2. Okay, now again, two oxygen normally, they are carboxylic acid and esters. Because these two functional groups, okay, these two functional groups, they have 2 oxygen. Okay, now that means H is carboxylic acid or ester, I is also carboxylic acid or ester. Okay, we're supposed to find out from the infrared spectra. Now let's go and look at the question. So I put H and I infrared spectra side by side like this so that we can see them more clearly. We are supposed to identify the bonds responsible for the principal peaks above 1500 wave number. Okay, so 1500 here, 1500 here. Now below 1500, we do not have to look at them. Now for both spectra, above 1500 wave number, there are 2 peaks. Okay. Now if you refer to the table given, okay, given in the exam question, this one belongs to the OH bond. Now here I have a peak also, but it is not broad. So this is not OH. Refer to the table, this is actually CH bond. Then this one that is very close to 1500 belongs to C double bond O. This is also C double bond O. Okay, so that is why, okay, if you look at the answer scheme for spectrum of H, okay, 2 main peaks, C double bond O and OH. For spectrum of I, C double bond O and CH. Right, just now we said that H and I, because of the molecular formula, okay, they are either carboxylic acid or ester. So look at H, yes, C double bond O is OH. So H is the carboxylic acid. Okay, I, you don't see OH bond, so I is an ester. Now let's solve the structure. Two carbon carboxylic acid, one of them must be the carbon of the functional group COOH, two carbon only. So the other three hydrogen and one carbon will be the R group. Okay, and okay, I functional group COO and ester. Okay, now O cannot be bonded to H. If not, it will become a carboxylic acid, right? So let us put a CH3 here. That means this part will be a hydrogen. So this is the structure of H, this is the structure of I, this is ethanoic acid. Okay, so I is this ester. Okay, the name of this ester is methyl because this is the alcohol, from the alcohol, and here from the carboxylic acid, from a methanoic acid. So methyl methanoate is the name of this ester. Okay, so part B of this question asks us to name H and I. H is ethanoic acid, I is methyl methanoate. So that is the end of this discussion.